Right, so here we go on the control laws and state space equations lecture. And let's look at the learning outcomes first. So the first thing we want to do is how to formulate a mathematical equation called the control law. In state space, one of the key features is the control law. You can do this for a linear time invariant system. And how to describe the control law with a state space representation and form a closed loop system. So we can take the control law, the open loop state space representation, and form a closed loop system. We're also going to look how to add in integral and phase lead states to the open loop state space models. In some cases, the controller itself has some states, in which case the size of the state space equations can grow. And finally, how to form a set of closed loop state space equations and assess the stability using eigenvalues. So this is an alternative method now to looking at stability. We can form the closed loop transfer function, look at the eigenvalues. If all the eigenvalues have got negative real parts, we can conclude it's stable. So the first one we're going to look at is the simplest one, which is output feedback under proportional control. So here's our state space representation. Here's a simple proportional controller. Here's a feedback control system. And if we look at the state space equations now, we've got x dot as x plus bu, y equals cx, and u now is kpe, but e is v minus y, because y equals cx. So we can get out that it's kpv minus kpcx. So we can combine that together to give us the closed loop state space equations. X dot is a minus bkpc times x plus bkp times v. Y is still cx. And the stability of the system now is a function of this part, because these now are closed loop state space equations. And so this is the closed loop stability, comes from this, the eigenvalues of this term here. And as a little example of this now, there's a mistake here. There should be a 2 here. So just imagine that's a 2, like it says here, 2. Got closed loop system under closed loop control of 2, and some state space equations under closed loop control 2 as well. The matrix we're going to convert this transfer function into is a companion form. So that's going to be 0, 0, 1, 0, 0, 1, then minus 6, minus 16 and minus 8 as the numbers along there. Then B will be 0, 0, 1, and C will be these numbers here in reverse order, 6, 8, 2, D will be 0. And we're going to form A minus BKPC, BKP and C. And if we were to put those into these equations now, into this block diagram, we've got building this up. So here's your closed loop system under transfer function under closed loop control 2. Here's a state space. This is an open loop transfer function here, but it's under closed loop control with a gain of 2 as well. So if we click, having built this up, if you click here now, some box will pop up. Now here you're going to put in A, B, C and D, because we've defined them here as A, B, C and D in MATLAB. But here, we're replacing them, we're going to work out the closed loop state space equations, which are these here. And so these now, if we click on this box, this will be ACL, BCL, CCL and DCL. These are the closed loop state space equations. Now, if we do all the analysis correctly, obviously all 3 outputs looks exactly the same like this. So that's what we're looking for, that we've done it all correctly. And if we look at the MATLAB code for this, I'm going to talk about the MATLAB code in a little video afterwards as well. This is the A matrices, B and C enter in here. This is forming the A minus BKPC. This is forming the BKP. And then this part here then takes the A, the B, the C and the D of the closed loop system and forms it into a system within MATLAB. Then TF can extract a transfer function, and ZPK will give us the transfer function in pole 0 form. Now what I've done here is, as a matter of interest, I've put this little transfer function into MATLAB and then put it under feedback control of 2 and then done a ZPK on that as well. So if the code works correctly, this transfer function here, ZPK sys2, should be the same as ZPK sys12 because they're the same thing but coming from a different point of view. So that's what we're going to look at next. Right, so this is our state space control and a proportional control, and before we do that, let's just look at the normal block diagram analysis. We would do this. So say we've got some proportional control here, KP, some transfer function GS here, and a feedback control system. Input V, output Y, error here V minus Y, and this signal here called U. That's the signal going into the transfer function. So we could say that the Y is the transfer function times KP times the error. So it's V minus Y times KP times transfer function equals Y. We can rearrange this now into our standard form, and we get the Y is KPZS over PS plus KPZS. So you can see there's quite a bit of analysis to do here. Some of it is non-trivial because it involves like polynomial mathematics. So the advantage now is if we move to state space, we could represent our transfer function this time by some state space equations. Now, in normal situations, the D is 0, but in some cases where it's not, so we have to bear in mind this is our transfer function represented. X dot is AX plus BU, Y equals CX plus DU, but in the main, the DU is 0. It's not always 0, but in a lot of cases it is. And so if we then got the same control configuration, so this is replaced now, if you like, by X dot is AX plus BU, Y equals CX. So this has gone into here. So E is still V minus Y, and U is KP because it's proportional control, which gives us that U is KPV minus KPCX. And this is the important bit. This is now called our control law, and this part of the course is all about control laws. This is the simplest control law we can have, and we can now put this U value into here. So that will give us now X dot is AX plus BU, so BKPV minus BKPCX. Now, one thing to bear in mind with when we're in the matrix domain, the order is important. So like 1 times 2 times 3 is the same as 3 times 2 times 1, but in matrices it's not. So the order in which these appear has to be preserved by the algebra that we've got here. So B comes first, then the U. So B comes first, then the U. So it's BKPCX. So we can rearrange this now into X dot is A, and then we've got these BKPC minus BKPC times X plus BKV. And this now is the closed loop state space equation. So this now is equivalent to this. But notice how simple it was to get to this point here. Certainly if you've got a computer to help you with this. So if we call this now, this whole thing ACL, and this whole thing here BCL, we could work out the closed loop transfer function as C into SI minus ACL to minus 1 BCL using our standard transfer function equation. So this equation here now is exactly the same as this. So hopefully you can see from this that this analysis lends itself well to an algebraic simplistic form, with a difficulty being that we've got matrices to manipulate. Now, because it's matrices, we can adopt MATLAB to do the matrix work for us. So that's the advantage of this method now. State space is good, but you need MATLAB to help you. Without MATLAB to help you, it becomes tricky. It's easier to do it this way, as like polynomial maths. But as these polynomial maths gets bigger, this gets more tricky. This method works. This will work for any complexity of A. So A could be 100 by 100, and it might take you a long time to do this by hand, but with MATLAB, you could do it in a jiff. So what I'm going to do next is to describe now how we can do this type of thing using MATLAB. Right, so now we're going to look at the MATLAB code now for doing these type of problems. So I've got three identical block diagrams. Here's proportional control of 2, here's a transfer function and a feedback control system. We could convert this into state space equations, and we could run that as a feedback control system, or we could work out the closed loop transfer function using state space with ACL, BCL and CCL, feed the input V directly into this and get the same output. So there's three ways now of running the same system. So the first thing we do is get the state space equations here. So that's going to be say x1 dot, x2 dot, x3 dot, and we're going to do the companion form here. It's going to be a 3 by 3. I'm just going to change my pen. Slightly struggling with pens this afternoon. Let's hope this one works. x1, x2, x3 plus u, y, x1, x2, x3. So there's our state space representation, and we're going to do this in companion form. So it's going to be 0, 1, 0, 0, 0, 0, 1, 0, 1. So that fills up like that. And then these numbers here are these numbers here in reverse order with negative signs. So minus 6, minus 16, minus 8. And these numbers here are those in reverse order, positive signs, 6, 8, 2. So we could go now from our transfer function to the state space equations here, and we could enter the state space equations into MATLAB by entering this as the A matrix, this is the B matrix, and this as the C matrix. And we've also got a plus 0 times U in there, so the D, if you like, is 0. So this will be fairly straightforward to do. Struggling with my pens here. Right. And so we can put A equals open square brackets and put this row in, so it's going to be 0, 1, 0, then a semicolon to indicate end of line, spaces in here as well. That'll be 0, 0, 1, semicolon, and then minus 6, minus 16, minus 8, close square brackets. So this is the A matrix in. We could then put B, open square brackets, 0, semicolon, 0, semicolon, 1. Every time we add a new line is a semicolon, so that's 0, 0, 1, 0, 0, 1. And C will be 6, 8, 2, and D will be 0. That's how I could now enter this state space equation into MATLAB. And the next thing I'm going to do now, so that could be some direct code I could type into MATLAB. That would enter my state space. I could then simulate this or this by entering A, B, C and D as the state space representations of these numbers here. I'll show you what that means in a moment when we come to do the MATLAB Simulink bit. But the next stage is to form this closed loop state space equation here. So that's our next little job. That'll take us a bit more time. So we remember this now, so I'm going to rub this out to get some space. And nothing seems to be working very well for me today. Unfortunately, the board isn't cleaning that well, but it does clean nicely with the cleaner. Now, if we remember back, the closed loop state space equation is given by A minus B KPC, and the B matrix was given by B times or KPB. So we need to form now these two things to form the closed loop state space equations. Now in this particular case, it's not true all the time, but the closed loop A is still a 3 by 3. Now there's one useful command, so I'm going to put ACL is zeros 3, 3. Now what this does is it makes a matrix size 3 by 3 and calls it ACL. I'm also going to put BCL equals zeros 3, 1. So these sizes now will vary with different problems. And we've got this equation now, so we can put ACL equals A minus B times KP times C. So assuming now we've got these in already, all we need now is to put KP in. So if I put in here KP equals 2, which is what we're doing, the KP equals 2, so my P's going with me there. KP is 2. It will now know what A is, B, KP and C, and so it'll work out ACL for me, not give me the closed loop A matrix. I can then put BCL, and that'll just be B times KP, so it'll just be B times KP. And then my CCL will still be C, and my DCL will be 0. So I've now got my closed loop state space equations in quite quickly, and I can put, say, sys1 equals SS. So SS takes a state space representation, a set of matrices A, B, C, D, and forms it as a system within MATLAB. So if I put this now as ACL, BCL, CCL, DCL, it's in round brackets. Then this will enter now this system, this closed loop system, as a system within MATLAB. And then if I want to get at the transfer function, I can say sys2, sys2, use the TF command of sys1, and then maybe do ZPK sys2. So what this will do is the SS command forms the system within MATLAB. TF converts sys1 into a transfer function form, and ZPK factorizes it out for us. So this would give us then a factorized closed loop transfer function. And if we changed KP to a different number, we could get a new closed loop transfer function. And so that's how now we could write some MATLAB code to actually form a closed loop transfer function, and also to get the closed loop transfer function out as a transfer function factorized. Right, so here's my MATLAB code for carrying out the closed loop proportional control system. Here's the block diagrams here. And so I'll be a bit lazy now, and I go and copy this code like that, do a copy, and then go into MATLAB and open up a script file. So do a new script file and paste this in, and then run this bit of code for us. So this is doing what we just discussed really. I'm going to call it SS underscore KP1. Save that. And first thing to look at is this has actually worked out. Here's the closed loop transfer function coming from the transfer functions, and here's the closed loop transfer function coming from the state space. So it's 8, 2, and 0.77, and we go down here, got 8, 2, and 0.77. So it looks like we've done it correctly. This is also entered in now. It's got an A, so if we type in A here, there's the A, there's the B, there's the C, there's the D. If I enter in ACL, it's formed my closed loop A matrix. actually it's not quite the same as the original A. Original A, remember, was this one here, so you can see it's changed it. If we type in BCL, get the closed loop B, and CCL, they're the same. So if we now go over into our simulation, so here's our simulation now. So this is the closed loop system with proportional control. If I click on this box, notice here I put A, B, C and D in here because these are the open loop. Click on OK. If I click on this box though, this has got ACL, BCL, CCL and DCL, and these have got the closed loop state space equations, and if you mix these up it'll go wrong. If we then run this simulation and we look at, I've got 3 outputs coming up on the same thing here. So if I look at an individual one, this one looks like that. If I look at this one looks like that. And if I look at this one, it looks like that. But if I put all 3 up simultaneously into the same little box, I can do that by doing, going to, let's see, signals and ports, number of ports, then choose 3. And then click on this, and again they're all superimposed on one another because they're all the same system. So that's showing you now how you can take proportional control block diagrams, proportional control block diagrams but with a state space in there, or forming the closed loop state space equations and then directly getting this. So this is quite a powerful little trick we can pull. And remember, going back to our, here we've formed the closed loop state space. SS converts them into thing, and then this takes SS, the TF converts it into a transfer function, and then ZPK-sys2 gives us the closed loop transfer function from the state space analysis. So if we type in ZPK-sys2 again, ZPK-sys2, we get, this is the closed loop transfer function now, when we've obtained that using state space analysis. Right, so here we are under output under integral only control. So there's no proportional, this is integral, and we've done that by putting a 1/s in here, which is representing the integrator, and we've got a gain Ki. So this will need now an extra state. So the difference between this and what it did before was the A closed loop A matrix will be one state bigger than the original state space equations here. So we have that the equation representing the integrator is that Z dot is equal to V minus Y, and that means that if you integrate this, you get that Z equals the integral of V minus Y, which is what integral control is. So that's our definition of integral control. And looking at state space now, I've got x dot is x plus bu. U is Ki times the integral of error, and we're making the integral of error equal to Z. So we get Ki integral of error is equal to Z, and that if we differentiate this equation here, we get that Z dot, if we differentiate the integral, it just becomes E. So there's our, which is V minus Cx. So we get x dot is Ax plus Bu, and Z dot is V minus Cx. That's this times this. So this time the state space has grown by 1, and these are the open loop state space equations. Now when we put U is equal to Kiz, this becomes U is Bkiz, and it fits in the Z state, so it's the Bkiz. So U is Bkiz, so it puts in that term there into this matrix. And these now are the closed loop state space equations with the integral. And the interesting thing about this really is that the states has grown by 1. So we've actually grown the number of states here. And this comes out as the system matrix. And then to get the stability of the system, we would look at the eigenvalues of that matrix there. Now we could do some analysis on this in a similar format to what we did before. So we're going to put a 1/s in here, put a gain of 2 in just for consistency, 1/s in there, and we could work out the closed loop state space equations as well, and simulate these to show they all represent the same thing, where the closed loop state space equations are represented by this set of equations here. Notice it's driven by a V now, not by a U, because that's the U there. And here's our code for doing it. So the original code here, that's entering in the original ABC, and then this time I'm making ACL 0 is 4 by 4. This is 3 by 3. 3 plus 1 is 4, so it's a 4 by 4. And B is a 4 by 1, and C is now 1 by 4. So the C is not the same as the C before. So now I'm going to have to copy now the A matrix into the first 3 by 3 slots here. So I've done that with two for loops. For N is 1 to 3, M is 1 to 3, A, CL, and M is A and M. So this, what that bit of code does there, it sticks that A into there for me, into the closed loop. This is ACL here, this big 4 by 4. This one, if we look at the B now, the B, well, next thing we need to put in this part and this part now. So I've done this for 1 to 3. A4n, so that's the fourth row, is equal to minus C n 1n. So that writes the C in there for me, this line of code here. And this line here, notice I've got, this is 4n because it's the fourth one down and goes n. This one is nth along and goes down by 3. So it's the 1, 4, 2, 4, 3, 4. That's 1, 4, 2, 4, 3, 4. That goes in that box there. So that's equal to B times Ki. And so that bit there does that bit, and that forms then ACL for me. Then I've doubled up the code here, so it doesn't, don't need that. Looking at the B now, the B for BCL, BCL is all zeros, but we've got a 1 at the bottom, so I've put BCL 41, it's the fourth one down, is equal to 1, so that BCL makes that B for us. And then the C, CL will be the same as the C for the first 3, but no Z's, so it'll be for 1 to 3, CCL is equal to CCL. Because we've made it zeros at the start, we'll just put a 0 in the end. So that's filling up the C matrix for me, and DCL is 0. And then we use the standard command SS to enter the closed loop state space equations. And if we do a TF command and a ZPK, we can look at the closed loop transfer function from that code. So that's the overall code. And this is then the simulation. If I click on this box here, enter an ACL, BCL, CCL, and DCL into this one, put an integrator in there from my previous example, and then when I run this, then I will get the closed loop simulations, again all looking the same. So we'll have a look at that in a moment in MATLAB. Right, so here's our state space problem now with integral controlling, so we've got 1 over S here and a gain Ki of 2, just to be consistent with our previous example. Well, that number could be anything we fancied. So because we've got an extra S in here, you can see the cubic and the extra 1 gives us a fourth, so we're going to expect a fourth order state space representation. And so we could represent that by converting this into state space and also working out our closed loop state space equations as well, and directly driving it without any feedback in, because this is closed loop. So state starts off with our state space equations for the open loop system. X dot is x sub u, y equals cx. U now is Ki times the integral of error, and Z dot is E, is our definition of the integrated state, because that, if we integrate this equation, integral of this gives us Z, integral of this gives us integral of error, so Z is the integral of error. So if we replace then the integral of error with Z, U becomes KIZ. So this is our integral controller, and if we now put, here's our X dot is x plus bu, Z dot now is E, which is V minus Cx. So X dot is A x plus bu, Z dot is V minus Cx. So that's that one. So let's just grow now to a, in this case, a 4 by 4. Then we have have to put the control law in. This is the control law, remember, for the system. Quite a simple one, but we're just building up here. So U now becomes KIZ, so this becomes BKIZ. So that's in the first line, so it's going to pick up a BKIZ replaces U. And this then forms our closed loop state space equations, which we can then put into a format suitable to go into MATLAB. So if we just clear this off a bit. It's a bit colder in my garage today, so the material isn't drying off the board as quickly as it might do otherwise. Right, so here you go now. So we need to form this matrix here. So we'll have A equals, that'll be our previous A, B equals, and C equals. This will come from the previous example. We're putting in the state space equations. This time this is going to be a 4 by 4 matrix, so I'm going to put ACL equals zeros 4, 4, and BCL is zeros 4, 1. Remember, it goes this way first, that way second. And CCL is zeros 4, 1. 1, 4, sorry. 1, 4. So there's my structures now. Now what I need to do next is into the ACL, I need to insert the A into this patch here. This is the first 3 by 3. So I'm going to do that with 2 nested for loops. So I have 4, say n, equals 1, step 1 to 3. For m equals 1, step 1 to 3. ACL nm equals a nm, and then an end and an end. So this end goes to that for loop, that end goes to that one. And what this code does, essentially, it writes the A matrix into that patch there for me. So that's giving me that one. I need the BKI in here now and the minus C in there. So I can do that with some more for loops. So we draw a line down there. So I can say 4 n equals 1, step 1 to 3, because the size of these is 3. And this is ACL now. ACL, and if I go for this one, this is going to be the 4th one down, and then that's fixed, and then I have to go that way 3. So it's going to be 4, n. That's going to be minus C 1, n. It's minus, and so when n is 1, it puts 4, 1 equal to C11 minus C11. When n is 2, it puts 4, 2, so the second one there, equal to C minus C2, so it's doing that sort of thing. And then we can have A, CL, n, 4. This one now, this one is the 4th one along, so it's going to be, this is going this way, and this is going that way, so it's the 4th one. So they're swapped around here because this is a column as opposed to a row, and it's the 4th, n has got to go 1 to 3, and it's going to be equal to Ki times B n, 1, and then an end. So this part here now will fill up there and there for me. And then once I've done that, then I can put that, say, sys1 equals SS, ACL, BCL, CCL, and 0. And that will then transform this into a state space representation in MATLAB. And then I can say that, say, sys2 equals TF sys1. And that will give me in transfer function form. And if I then put ZPK sys2, I will get out the closure transfer function factorised into poles and zeros. So here's the code for forming this in MATLAB now. Notice I'm using 4 loops here, a bit of 4 loops there, and another 4 loop here to write in the A and the minus C and the BKI. So that's something new that you might not have met before, but we will need that skill for doing most of the examples. So there's the MATLAB code now with some description for you as to how to do it. Right, so here's my integral controller with these are the 4x4 matrix now with this is the generic state space equations. This is the code I've just described. So if we take this code now and so I can copy the code, do a copy, then go into MATLAB and I can open up a new script file and then I can paste the code into there, then run it and stay away. Let's run it again, didn't like the name. Here we go, and I can check some things out here. I can type in the A, there's the A, there's the B, there's the C. I can get ACL, there's my closed loop. Notice now it's a 4x4. BCL should be 0001, and CCL is the one with a naught in here. So it's formed the correct ABCs for me. And if I now go into MATLAB, and this is now my closed loop simulation, so notice I've got the integrator in there, gains of 2. This one is my, remember this is my open loop A's, these are my closed loop A's, and if I run this now and look at the single output here, you can see they're all exactly the same. So showing that these 3 systems now, this is a block diagram system, it's a block diagram but with the open loop state space in here, and here now is your closed loop state space equations. The closed loop state space equation, remember, are formed from these matrices here and this MATLAB code to form your closed loop state space equations. So that's another example now with integral control and extending the state by one extra value. Right, so here we have a combination now of proportional plus integral control, which is really a linear combination of the previous 2 that we've done. So we take the proportional controller plus the integral controller, we can rewrite this in this more useful format for our state space representation. The KP is the proportional control and this is the integral control. So this is our rewriting of this, they're both equivalent. And so now we've got proportional control plus integral control controlling the system. And if we move on to our state space equations, x dot is x plus bu. U now is kp times the error plus ki times z, where z dot is v minus cx. So this is z, remember, is the integral of the error. So x dot is ax plus bu and z dot is v minus cx. So that's our open loop state space equations. Then we apply our control law now here into here. So this is going to put a b kp and a minus cx. That's going to be b kpc minus where the x is. It's going to put a bki with the z's, so those go in that way. We also get a bkpv, and so these now form the closed loop state space equations. And so here now are our closed loop state space equations, and the stability is given by the eigenvalues of this matrix here. So we could now have a similar example, same system, but I put a proportional gain of 4, integral gain of 10 on here, and we're now going to build up the simulations of these, but also work out the closed loop state space equations for this one with the PI controller set to proportional 4, integral at 10. So here's our code now. So it's very similar to what I had before. Really. This sets up the A matrix, the original A matrix. Here's our Ki as 10, Kp as 4. It's a 4 by 4 matrix that sets up. Then we have A is A minus B Kpc. So this is exactly the same as what we had before. We've got this is working out the C and also the BKP. So it's working out this part here, working out the C and the BKI. The C and the BKI, they come in here, very similar to the integral control we just done, and then the we've also put in the B now. That line's doubled up, isn't it? Shouldn't be there. This B is equal to the BCL is BKP, so that's the B times KP. We feel that's going to be in those first 3 rows of B. First 3 rows of B here, BKP in the first 3 rows, and the bottom is going to be a 1. So we're looking for B41 to be 1. And this fills up the C, and there's our state space now, closed loop state space of this system. And then if we wanted to, we could convert this into a transfer function and get the closed loop transfer function as well. But let's have a look now at the MATLAB code for this. So just got a bit confused here. Here we go. So what I'm going to do now is get my code here. So if I get this code here and copy this, do a copy, then go to MATLAB and do a new and script. And I've got the wrong size of screen now, but I'll re-get this, paste it in, and there's our code there. So if I run this now, I should be able to see down here now ACL. There's our ACL. Remember, that's our original A. So ACL has got this, has got the closed loop part in now. That's the BKI in there. There's the minus C in there, and there's the A minus BKPC in there. If we type in BCL, there's the no, that's down the KP, because KP is 4 and the 1 in there. So there's those terms. Then go into our Simulink simulation now. Unfortunately, I'm lost a little bit on the left hand side here, which I can't really change the size of very quickly. But anyway, here's the gains of 4 and 10. Here's the other ones with 4 and 10, and this is the closed loop system now. So if we now run this one and we have a look at the 4 outputs or 3 outputs, here's now the step response of all 3. So you can see if there was a mistake in here, say for instance that was a 3, so there was a difference in them. Now when we run this, we see we get 2 slightly different graphs because one would be different to the other. But by having all 3 the same, we know now that we've done it correctly. And this is the closed loop system under PI control. This is the state space under PI control, and this is the closed loop state space equation. So we click on this one. There's this using ACL, BCL, CCL, and DCL to get the state space representation, and that's giving us the same output as the other one. So we just go back. Unfortunately, it's covering my screen up a bit. We go back to here. So this is now our proportional plus integral closed loop state space equations. A minus BKPC, BKI, BKP minus C naught I. This is the closed loop stability, and this is how we could write some MATLAB code to generate this closed loop state space equations under PI control.